Okay, in this lecture, we will try to understand the bipolar junction transistor. So let's try to understand what is this bipolar junction transistor. So in a bipolar junction transistor, I have an N-type material and I have a P-type material and I have another N-type material. Okay, so basically I have two PN junctions here. Okay, and this N-type material is called emitter, and this middle one is called the base, and this one is called the collector. Okay, so we'll see why the name it as emitter and this is collector. The reason is basically this will emit the carriers and this will be the collecting. Okay, so and we have of course three terminals here. Okay, to access these emitter, base and collector. Okay, and of course these terminals are named sometimes as C, B and E. E for emitter, B for base, C for collector. Okay, so now even though this two looks to be two PN junction, we have this PN junction here and the other PN junction here, it looks like a back-to-back diode. But note that if I just connect two diodes, something back-to-back like that, and call this as collector, call it as base and emitter, the operation of this BJT and this kind of configuration, note that is not the same. Okay, so this has to be very clear. Okay, secondly, although this may look symmetric, like the emitter and the collector, they may look symmetric, but it's not so. Doping concentration of this emitter will be much higher compared to the collector as well as the base. So this also we will see eventually. Okay, so now I have this NPN type of transistor. Okay, then we can have also other kind of transistor which is PNP, right? So which is basically having a complementary property compared to this NPN type of BJT. So the conclusion is there can be two types of BJTs. One is the NPN and the other is the PNP. Okay, and of course, once we know how this NPN operates, understanding how does this PNP transistor operates, it will be very simple. Okay, so we'll focus on trying to understand how does this NPN operates, and the PNP operation is also quite similar. Okay, so now of course here we have two PN junctions as I was mentioned before. One is this one and this other is this one. So now as we know that the PN junction can be in forward biased or the reverse biased. Okay, so if you see here I can have multiple combinations. Either this PN junction can be in forward biased and this also can be in forward biased. This can be reverse biased and this can be in reverse biased, and of course one can be in forward bias, other can be in reverse bias. This can also be in forward bias and this can also be in reverse bias. Okay, so we have different kinds of combinations. Okay, so now it has been observed or it has been seen that the scientists who have invented this transistor, okay, so back in 1948-47, so that when this is in forward bias and this is in the reverse bias, then we will get very useful property. Okay, so finally so we will be biasing this portion, right, the emitter to base in forward bias region and the base and the collector in the reverse bias region, and this will lead to a very useful property. So let's look that in more details. So I'll be connecting a voltage between this base and the emitter. So we will call it as VBE. Okay, so because this is a potential that is connected across the base and the emitter. Okay, and So this is the BBE, and I'll connect another more potential here, okay, which is basically VCB, and as I was mentioning that it will be in the reverse bias region, okay. This will be in the reverse bias region, okay, and as I was mentioning, this will lead to very some useful property, okay. So yeah, so here important conclusion is that the emitter and the base will always be in forward bias region, and the base and the collector will always be in the reverse bias region, okay. Okay, so these are the two conditions that we should follow. Now, depending upon how much voltage that I'm applying here and here, it will lead to basically three different types of region of operation of this transistor. Okay, depending upon how much I'm applying this VCB and VBE, how big, how small, we will see that. So based on that, it will lead to three different regions of operations. Okay. Okay, so based on the value of the BB and BCB, there will be three different regions of operations. So these three regions of operations are: one is the cutoff, the other is the active, and the third one is the saturation. Okay, so these are the three regions of operations of the transistor. And mostly when we will be designing different kinds of analog circuits, right? So we will be focusing in the active region of operation. Okay, definitely when we are dealing with some digital circuits based on the BJT, we may use this cutoff region as well, and sometimes the saturation region may also be used, but most of the time, majority of the application, we are supposed to keep the transistor in the active region of operation. And then these are like the boundaries, we have to make sure that the transistor never goes to the cutoff region, and also we have to make sure that the transistor never goes to the saturation region. Okay, so these two are sometimes the forbidden region, and we will be mostly focusing on the active region. Okay, so let's try to see what happens to the transistor when it is in the active region of operation. So this is my transistor, and now we will be discussing about the active region. So now, as we know, right, if there are two PN junction, there will be depletion layers, and when these, especially in the forward bias region, when a forward bias voltage is applied, there will be a reduction in the depletion layers, and there will be flow of the current. But note that the doping concentration of the emitter, this is much much higher than the doping concentration of this base. And from our discussions on the PN junction, we know that wherever the doping concentration is less, the depletion layer will be higher. But of course, since we have depletion layer, will be the width will be higher. Okay, and of course because we have applied this VBE, so of course it will be much small. But of course this side will be smaller. Okay, this side will be smaller. This side will be a little larger. Okay, correct. So but of course this with the application of this voltage, definitely this is going to reduce again, depending upon how much voltage I'm applying. So it will become very small and the current starts flowing. Whereas because this base and the collector is in reverse bias region, so I'm supposed to have a large with depletion layer, and there will be an electric field, okay, in this direction, electric field, strong electric field in this direction. Okay, so now because this emitter has lot of electrons, right, so there will be a diffusion current because of this, right, because of the application of this forward bias voltage. So let me represent the flow of the electrons from here to here with this blue color, and I'm showing a thick arrow here showing that there are a lot of electrons are going. Okay, a lot of electrons are going from here to here. Okay, whereas if you see the holes are very less here compared to the electrons, So the hole current, because of the diffusion of the holes from here to here, because of the reduction of the barrier, it will be much smaller. So let me show this one. Okay, and now these electrons will try to recombine with the holes. Okay, but only few will recombine, because as we know that the number of holes is much lesser compared to this one. So a lot of electrons will be here, but as soon as this electron reaches this, this surface here, because we have a strong electric field in this direction, this will be swept away to the collector. Okay, so these electrons will get swept away further to the collector by this strong electric field. Okay, and yeah, this will lead to a collector current IC. Okay, and of course the electrons which are recombining with the holes, as well as the holes that are diffused to this emitter region, it will lead to a small base current IB. Okay, okay, and of course this is IC. C stands for the collector. Okay, and of course we know from the simple KVL principle, if we can neither create current or we can destroy current, so this both current together will lead to a current IE, which will be summation of this IB plus IC. So basically what has happened is, because we have a lot of electrons here, and because of the reduction in the barrier potential, this has been diffused here, and few of them have recombined and formed this IB current. And of course, if you see the direction of the current is opposite to the direction of the flow of the electrons. Okay, so the electrons is flowing in this direction, so this is leading to this IC current. Okay, and the holes are flowing in this direction, so it is in direction of this IB, and the recombination current is this because of this electrons getting recombined. So the current direction, overall current direction of this current component is also this one. Okay, yeah. So this is what is happening. So actually what is happening is, if you see here, this voltage VB is opening the barrier, and huge amount of electrons is coming, but this base, because of its low doping concentration and at the same time very small width is much smaller actually. So because of which it is not able to capture all the electrons that is coming here. So only that's why this IB current will be very less. Whereas this, because because of the strong electric field, all the electrons are getting swept away. So that's why this IC current will be much higher than IB. Okay, and if you do an experimentation and a measurement, what we'll see is that this current IC will be beta times IB. Okay, so and this beta is approximately around 50 to 350 or even more, right? So because we know that a lot of electrons has come here, and there is an electric field E, and depending upon how we are selecting the doping concentration and all, so this beta factor can be 50 to 350. Okay, and of course this current IE is equal to this current IB plus IC. Okay, so one may ask, one may try to understand how conceptually this is working. So basically what is happening is, this is trying to open the barrier, but it is itself is not able to absorb all the electrons that is coming, but this electric field that is there, the strong electric field is absorbing all the electrons. So this can be understood by this simple analogy. So suppose I have this lot of water is here. Okay, a lot of water is there, and this water reservoir here, maybe thin reservoir, and maybe I'm restricting this flow of this water by a small pipe, something like this. Okay, of course this is a very crude example. Okay, this is a very crude example, and it is currently it is stopped. Okay, so now what is happening is, what I'm trying to do is, I'm trying to lower this barrier so that water can flow out. Okay, so I'm lowering this barrier. Now because of this lowering this barrier, what will happen is, water is going to flow out. Okay, huge amount of water, and because of this barrier some water also will flow through this pipe, right? Okay, through this pipe, but you can see that a lot of water, more amount of water is going to flow outside compared to this one, because yes, it has reduced the barrier which was stopping, the flow of the water, but and the water is flowing out, but in itself it only very less amount of water is flowing. So this is the base current, and this large amount of the water flow is the collector current, and this is IB and this is IC. Okay, so this is a very crude example, but actually this is what is happening. So coming back to the operation of this transistor, if you see here, this this PN junction, the junction between the base and the emitter, is in the forward bias region. So this base current will follow the same principle as the diode. Okay. So what I mean is the relationship between this IB and BBE will be same as the equation that we had, right? Some Is into e power PBE by VT. Okay, so VBE is the potential across this PN junction in the forward bias region. Okay, and this is the VBE. Okay, is the potential, and yeah, so IS, yeah, so IS is the reverse saturation current. So let's just put IS there to make it different than the diode. Okay, so yeah. Okay, so this is the base current IB, and it will follow this exponential relationship just like the normal PN junction diode in the forward bias region. And note that whenever you are solving any BJT related problems, we will be treating, and this part lies just like a diode, right? We'll be using the constant drop model, we'll be using how to calculate the small signal resistance RD. So all this will be applicable for this part of the BJT. Okay, this will be same as the analysis of the PN junction diode. Okay, and of course here I can substitute this whole thing in the first equation. So my IC will be equal to beta times IS dash e power PBE by VT, and this whole thing we can write it as IS e power PBE by VT. Okay, implies. Okay, okay, so we can definitely find out this IS, and we can derive, and it basically depends on the area of cross section of the base and the emitter, and the doping concentration of the base, and and width. Okay, but we'll not be covering in this course. You can refer to the Cedra Smith book when if you want to find out the derivation of this IS. So here we'll more focus on the application or use of the BJT. Now, if you see here, this IC is exponentially related to VBE. So IC is not at all related to the voltage VCB, right, which is applied at the collector. Okay, so what it means is that, so even if I vary this VCB, my IC is not at all changing. It is constant. It is just dependent on this voltage. Okay, so this is one of the very important property of the transistor. Okay, so this current IC is only dependent on this VBE, and it changes exponentially. Okay, okay, so now we will see the symbol of a transistor. So we will see how to represent a BJT. So this is my BJT. So this is represented by this symbol. I have a line here, and then another line with an arrow here. Okay, and this one. Okay. So this is my base, this is my collector, and this is my emitter. Okay. So in the region of the emitter, there is this arrow. Okay. So it is, you can remember as if because this is a PN junction and base and emitter are used in forward bias region. So it is something like a diode, something like this here. Okay. So this part, okay. So it will be used in a forward direction, and the arrow, basically this arrow of this direction represents the direction of the current because this base and emitter will always be in the forward bias region. So this is my collector, this is my emitter, and this is my base. So now let's try to characterize this transistor. Okay. So we will see the characteristics of the BJT. So first we will see how does this IB current varies with the VBE. So let's construct this circuit first using the symbol that we have defined. So this is my BJT. I have my base, this is base and this is emitter, okay? And this is the collector, so this is the symbol of the BJT. And we know that the base emitter junction is always in the forward bias region, and I have to apply a voltage which is VBE. So I have applied a voltage VBE, okay? And of course, we were seeing that the base and collector should be in reverse bias region. And if you remember, I have applied this battery here, BCB, okay, to keep this one in the reverse bias region. So instead of connecting a battery something like this, we will be connecting with respect to the VCE. Again, this is also the same thing. We are trying to make this base and collector in the reverse bias region. So I'm applying a voltage VCE, right? Instead of VCB, I'm applying a voltage VCE, okay? So again, this is also I'm applying a positive terminal here, and I'm making sure that this base and collector, they are in the reverse bias region. So I'm keeping this VC voltage sufficiently high, okay? So now we will do two types of characteristics. We'll try to see how does this IC current varies with the VCE, and how does this IB currents varies with the VBE. Okay, so in the first characterization, what I will do is that I will keep this VCE fixed, and I will see how does the current IB changes with the VBE. So this voltage is fixed, okay, and what I'm doing is I'm observing this current IB current, right, by changing the VBE voltage. And of course, if you see here this region, we know that this is a forward bias PN junction, and as we have discussed before, it follows this expression, right? IB equal to IS dash e power VBE by VT, okay? So same as the diode, okay? So in this case, I have IB is equal to IS dash power. So this is the thing that we are going to get in this, so this is the characteristic equation that we are going to get if I change the VBE, okay? So this is my IB and this is VBE, okay? And if I slowly increase my VBE, this is going to grow exponentially, just like the characteristics equation or the characteristic graph that we have seen for the PN junction diode, okay? And of course, in this case also we can approximate this whole behavior with is VBE on voltage, right? And this VBE on voltage is, we know that it is around 0.7, okay? So whatever the analysis that we did for the diode, all are applicable for this part of the BJT, okay? This is very important. So whatever the analysis that we did, right? So the same can be applied for the base emitter junction, because it is a simple forward biased PN junction, okay? And we can also approximate this whole thing with a straight line at BBE equal to 0.7, okay, just like we did for the diode. So now we will discuss another characteristics of BJT, which is IC versus VCE. Okay, so in this case, I'm keeping this VBE fixed, or fixed. Okay, and I'll be varying this VCE. Okay, and I will see how does this current IC varies with this VCE. Okay, we have seen that this IC current is equal to beta times IV, and of course IV we know that it is beta times IS e power IS dash e power VBE by VT. Okay, so if you see the expression of IC, it is independent of this VCE. So if I draw the characteristics curve of this BJT, IC versus VCE, I am supposed to get a straight line, because how much ever I vary this VCE, my IC is not going to change. Okay, and of course in the actual transistor there may be a slight slope, but for time being we'll consider it to be a straight line, so it is almost independent. This is because, as we have discussed even in the PN junction, right, the carriers that is drifted because of this electric field, it doesn't matter what is this electric field, it just drift that side. Okay, as soon as all the these carriers comes here, it just get drifted to the other side, whatever may be the electric field. So the current is mostly defined not by this electric field, but by the amount of carrier concentration that is there in the base. Okay, and of course, yeah, there may be some dependence of this electric field, which we will see later on in the later stage. But time being, we are assuming that it hardly is dependent on this electric field. Okay, so this is my IC. Okay, okay, so this is the variation of my IC with the VCE. Okay, and of course, if I have some other value of BBE, so this is for a particular value of BBE. Let us call it BB1, and of course we have this current is basically, I should say that this is IC1 is beta times IB1. So for a particular value of BBE, I'll have this IB1. Okay, and this IC1 is beta times IB. Okay, and if I increase my BBE to some other value, right, this is maybe BBE2, right, so where my BBE2 is greater than BBE1. Okay, and of course this is for you know this IC2 is equal to beta times IB2. Okay, so this is for another value of IB. Okay, yeah. So now one may ask, what will happen if I reduce this VCE to 0? Does this line is going to intersect here? The answer is no. If I reduce this VCE too small, it will be something like this. Okay, finally it will come to 0. So basically what it means, after some voltage, so this voltage is generally small, it's around, I should say that 0.3 volt, so it's around of this range 0.3 0.2 volt. Okay, so after this voltage, the IC will be dependent on the VCE. So this region where my IC is very much dependent on VCE is varying, this region is called the saturation region. And this region where my IC is independent of VCE from here to here, this region is called the active region of operation. Okay, so this is the active region of operation. Okay, so and if you see in the previous curve, okay, So IV was very small when this VBE was very small voltage, okay, and suddenly at some point it has increased, okay. So the voltage when the VBE is very small, maybe lesser than, I should say that lesser than maybe 0.6 volt, okay, my IB was almost equal to 0, okay. So when my IB, so when my VBE was less than 0.6 volt, you know, my IB is approximately equal to 0, and this region is called the cutoff region. Cutoff region is basically, there is no current, basically current is cut off because the IB is 0, so IC will also be 0, okay. So this region is called the cutoff region, okay. So let's summarize the different regions of operation, okay. First of all is the cutoff region. In this case the VBE is less than 0.6 volt, okay. And what is the saturation region? My VCE is approximately less than 0.3 volt. Of course, this is just a typical value. It may be little lesser than 0.3 or little more than 0.3 depending upon the structure of a BJT, but the value is around this. So both this should be satisfied. The VBE should be greater than 0.6 and VCE also should be greater than 0.3 volt, okay. So both of them should be satisfied. Of course, for the cutoff region, no matter what may be the VCE voltage, if the VB is less than 0.6, it is cutoff region. Similarly, for the saturation region, no matter what may be this VBE voltage, if the VCE is less than 0.3, then it is in the saturation region. However, for the active region, I need to satisfy both this condition, that the VBE should be greater than 0.6 volt and the VCE should be greater than 0.3 volt. Now let's discuss about the small signal model of a BJT. Just like we have discussed the small signal model of a diode, we need to discuss the small signal model of the BJT. In fact, this is very important because we are going to apply some signal in the BJT and see how it is going to act as an amplifier. Okay? Okay, so what we are going to do is that along with this DC voltage, we are going to apply a small signal voltage here, okay, and to understand its behavior, and accordingly we will model it, okay. So I have applied a small signal here, VBE, okay, and because of this, there will be a small change in the current, okay. So because of this DC voltage, so when my this VBE was 0, it was not there. Because of this DC voltage, I had this DC current IB, which is represented by capital letter I plus and capital letter B, and because of which there was this IC current, which is of course beta times IB. Okay. Now, because I have applied these additional small signals considered to be maybe few millivolts, right, there will be change in this IB current, and let's call this as by small IB. So I have this IB plus the small IB because of this additional VBE applied, and of course we will have also variation in the IC, and there will be this small IC, and we know that this variation small IC will be equal to beta times this small IB. Okay, so what I can write is the my small variation in the IC is equal to beta times small variation in IB. Now, of course, let's consider this whole thing. We know that this IB plus this small IB, the whole thing is, we know that this is I small b. Okay, this is the representation, right? and this is I small c, okay, right? So let's try to draw again the characteristic curve of the IV versus this VBE, okay? And of course the summation of these two is VBE, okay? As again I'm repeating here, this is very important, the notation is very important. So the when the this variable is capital letter and the subscript is capital, it is a DC voltage, DC no change. And when both of them are small letter, that means it is just the AC signal, the just the change, it has 0 DC value. And this IB is basically this capital letter I, and the small letter subscript, it means that it is the summation of the DC as well as the AC. So this is the actual overall signal. So what I'm doing here is that I'm plotting this one, right, the actual overall signal. So if I am increasing this one, so it is basically it will have this kind of characteristics. The exponential characteristics that we had seen before, because it is basically the following the exponential law. And let's try to find out at this point, okay, so this point may be the, so at this point it is VBE, it is the DC value, okay, DC voltage, this VBE voltage, okay, and corresponding to this, of course, I have my this DC value IB, okay, and on top of that there is a small change in the VBE, and there's a small change IB, okay. So now what I want to do is that I want to find the ratio of this small change IB with respect to this VBE, and just like in case of the diode, what we did is we have found out the slope here. And because this is like, as I mentioned, this is a PN junction forward bias region, it's like a PN junction diode in the forward bias region. So if I try to find out the slope at this point, okay, which is the slope at this point is given by, we know that is 1 by RD, right? So where we know that RD is equal to VT by this IB. This we have derived when we discussed the diodes or the PN junction diode. We have derived this expression, okay? And of course, instead of RD, because we are now dealing with this transistor, we are using another, we will use another subscript, okay, instead of RD. So we will be using R pi, okay, instead of RD, just to distinguish that this is for transistor, not for the diode, okay. And of course this pi and the D, and of course this R pi and the RD are the same, there's no difference. You can see that the expression is the same, okay. So not that, so R pi for BJT is similar to RD of diode, okay. That's why the expressions are also the same, okay. Yeah, and of course what we have seen here is the change, right? We can find out the change in this IB will be just the multiplication of this x-axis change with a slope, okay. So IB is equal to PBE by R pi, okay. So this is same as the small circuit analysis of the diodes, okay. So finally, if you see here what we got, we have these two equations for this BJT. One is the IC equal to beta times IB, and this IB is equal to BBE by R pi. So what I have is my IB is equal to BBE by R pi, and my IC is equal to beta times IB. So these are the two equations that we have got for the BJT, and these two equations capture the relationship between these three changes. The BBE, and which has produced this small IB, and because of the small IB I have this IC, okay. So let's try to represent this basic two equation with a simple model, okay. So We know that in case of a diode, we have represented this equation with a resistor, right? Okay, I have this resistor I pi. So here also I can represent this one with a resistor where I have a resistor I pi. If the current flowing through this is IB, okay, the voltage developed across this one is this VBE, simple Ohm's law, okay. And on the other side, okay, on the other side I have a this one IC equal to beta times IB. This can be represented by a current dependent current source. So this is a current which is dependent on the other current IB. So I have a current dependent current source here. My IC is equal to beta times IB, okay. So this is my current IC, okay. And if I name these three nodes, this is nothing but my base, this is my emitter, and this is my collector, okay. So this is because of the small signal VBE, okay. I have this IB is created, and this IB is given by this expression VBE by R pi, and this results in a current IC which is equal to beta times IB. So this is a simple model which we will use again and again to design different kinds of analog circuits and analyze a BJT, okay. And here's, of course, if you see here, sometimes this question is asked, why there is no connection between these base and the collector. So we know that the potential or the change between the collector and the base doesn't affect neither this IB or IC, okay. So right, so here we have seen that whatever this VCB voltage, which is actually also same as the change in the VCE, only the reference is the different, yeah. So instead of base, I'm considering the emitter, okay. So whatever maybe this voltage, it doesn't change neither this IC nor IB. So basically this voltage doesn't affect anything, okay. So that's why in my small signal model, these two, there is no connection or nothing, no component is here, okay. So all the variations that we have discussed are captured by this model. Okay, so in the next lecture we will use this model and try to design a basic first type of amplifier, which is the common emitter amplifier. Okay, so thank you.